Okay, so we just did a linear equation in the last video, and an extension to the linear differential equation. There's an equation called a Bernoulli equation. Let's see what happens when we we just solved a linear differential equation where the differential is to the first power and our y variable was to the first power. Now the first step in solving linear differential equations is setting it up to look like this. And notice that the differential is to the first power and the y is to the first power. So if we multiply both sides by y squared, these will cancel out and we'll get this on this side. So multiply both sides by y squared, we get y squared dy over dx plus 2y cubed is equal to x. Now notice, in order for us to use the linear differential rules, there must be a 1 right here, and this must be to the first power. Well, we have a 3, this y is to the third power, and we also have a coefficient in front of the differential, which is y squared. But the differential is still to the first power, so we can use what they call the Bernoulli equation. What the Bernoulli equation is basically like a U substitution. So let me erase this to get it a little bit more cleaner. This is to the third power. What we're going to do is we're going to let some variable, let's call that v. We're going to let v equal y cubed. Now notice, if we let v equal y cubed, look at this. Look at this y. This y is y squared, which is, if we take the derivative of y cubed, we'll obtain y squared. But we're also going to be using implicit differentiation. So if we let v equal y cubed, dv over dx, we're going to be integrating with respect to x, is equal to, take the derivative of y, and we have to multiply it by dy over dx. So we're going to be letting y cubed equal v. And what is dy dx going to be? Well, if we isolate dy over dx by dividing by 3y squared, we're going to get 1/3 y to the negative 2 power dv over dx. Now substituting in dy and y, I'm going to substitute it in green so that you could see it. This is 1/3 y minus 2 dv over dx. And we have this y squared. We're going to add to 2 times v. And then we're going to equal x. Okay. Now, why did we do that? If we look up here to a linear differential equation, the differential needs to be to the first power and the dependent variable needs to be to the first power as well. Now, what is our independent variable here? Well, notice that we have a differential equation with respect to x. So our variable up here would be the dependent variable, and they're both to the first power. And so when we let v equal this y cubed, notice that this y squared and this y negative 2 becomes, they cancel each other out. And then if we multiply both sides by 3, all in one fell swoop, we will obtain a version of the linear differential equation, and we can use the properties of a linear differential equation. Now to check, we have dv is to the first power. Our dependent variable is to the first power, and everything looks good. So now we can use the properties of a linear differential equation. It's already simplified. So step 1 was simplify. We already did that. It's already looking like this looks like that. So we're good. Step 2 is we're going to use the mu function to find the equation that we can multiply this differential equation by to do the reverse product rule. So let's identify what p of x is. P of x is the coefficient in front of the dependent variable, and right here p of x just happens to be a constant 6. Okay, that's not bad. So let mu equal e to the integral of 6 dx. Any integral of a constant, you just tack on that x, and there you have it. Our function that we multiply this linear differential by is going to be e to the 6x, e to the 6x, e to the 6x. So this is dv over dx plus 6v is equal to, and then we have a 3x here. Take a second to process. Now, remember in our last video when we multiply by some function, we need to do the reverse product rule, which is the derivative of two functions multiplied by each other is going to be equal to the derivative of the first function, copy down the second function, add that to the derivative of the second function, and we copy down the first function. Normally we go this way in differential equations. Specifically with linear differential equations, we're going to go the opposite way. So let's identify our variables. Now dv over dx, we're going to call that, let's use green. dv over dx will be our f prime of x. So that must mean that e to the 6x, and we're looking over here. We're looking at this stuff. E to the 6x must be just gx. So if f prime of x is dv over dx, then just v by itself must be f of x. So that means that all of this stuff must be g prime of x. Now we could check that. We check it by saying that g of x is equal to e to the 6x. Therefore, g prime of x must be equal to, remember we copied down the function, and then we take the derivative of the inside. And what we obtain is 6e to the 6x. So is g prime of x 6e to the 6x? If we look up here, it is. It's a little funky, so let me just clean it up and do e to the 6x dv over dx plus 6e to the 6x times v is equal to, and let's put this 3x e to the 6x, like that. So now you could clearly see that it does satisfy what we're trying to obtain. So that means that we could simplify this. Remember, we located this, so now we're going to just simplify. Now we just want the functions. So let's identify our functions again. This is f of x, and this is g of x. And we're just saying that we're going to take the derivative of f of x times the g of x function. So we simplified the left side. The right side will still remain 3x e to the 6x. And if we integrate both sides with respect to x, the left side, this dx will cancel with this dx. This integral will cancel with the differential operator d. And we're just left with v times e to the 6x. We haven't done anything on this side, so we're going to keep the integral. We're going to throw that constant outside of that integral, and we're going to get x e to the 6x dx. Now, similar to our last video, we're going to use the tabular method, where we're going to take the derivative of x, and then we're going to integrate e to the 6x dx. Now the derivative of x is 1, and the derivative of 1 is 0. This will be plus minus plus. And taking the integral of e to the 6x, I usually just take the easiest way to do this is you take the derivative of e to the 6x, which is 6e to the 6x, but I need to divide by 6 in order to get back up here. So when you take the derivative of this, you'll get 6e to the 6x over 6. These will cancel, and we'll get this equation right here. So that's how you check it. So that looks good. We're going to need to take another integral. Again, just real quick, you do the derivative e to the 6x over 6 times 6. In order to get it to a 6, we need to multiply by 6 in order for these things to cancel and for us to obtain that. So what that means is this 6 is going to be squared. To QC check this, take the derivative, you'll get 6e to the 6x, 6 squared, this square cancels, and we are left with what we started with. So we start with this point up here, we go diagonal. If we do another integral, this will just be equal to 0, so we don't have to worry about that. Doing the tabular method on the other side, notice that when we did the tabular method, we neglected the 3. So this 3 remains. This 3 stays, and it's going to be multiplied by x e to the 6x over 6, and that's a positive. Then we're going to have a negative e to the 6x over 6 squared. And the other one is going to be 0. This is going to be plus c. And whatever's left over here. It's very important for this c to be here, because when you divide by the function e to the 6x, it must be tacked onto that constant. So, like the previous video, we're gonna QC check this because I don't like using the tabular method because of simple sign mistakes. So we let u equal x, dv equal e to the 6x, and du is equal to dx, and v is equal to e to the 6x over 6. We do our cross. X e to the 6x over 6 minus, this is uv minus integral of v du. So this 1/6 goes out, dx. Take the integral of 6 to the e to the 6x. It's 1/6 multiplied by e to the 6x over 6 plus c. That's a minus x e to the 6x over 6. We simplify, this is x e to the 6x over 6 minus e to the 6x over 6 squared plus c. Let's look up, see what we got. Looks good. Now the only reason why this c is not inside these brackets is because if I multiply 3 times c, it'll be just some other constant k. So it's almost pointless to do it. It just makes things easier. You just realize that whatever you multiply by that c, you could just let it be another constant. That constant will be there no matter what. So let's divide by e to the 6x. E to the 6x. We're left with v is equal to let's see, 3x e to the 6x and then we're gonna multiply that by 6 minus e to the 6x, and now we could put this whole thing under 6 squared, and that's over e to the 6x plus c over e to the 6x. All I did was made this fraction into one fraction by multiplying both sides by 6 over 6. Now we have common denominator, and which is 6 squared. And then I factored in this 3 here, and factored in this 3 here, and everything looks good. Simplifying it a little further, we could factor out a 3e to the 6x, 3e to the 6x, which seems kind of silly because we just factored in that 3, but okay. We're left with x. If we take out these two, all we're left with is x. And the 6. So we have 6x right here. If we factor out this e to the x, all we're left with is... Actually, we're factoring out the 3e to the x, so this is just simply minus 1. And then we're left with 6 squared e to the 6x. Then we notice the 6 e to the 6x cancels. And just trying to make this look as pretty as possible. So this looks good. So we found our v function, but what did we let v equal? All the way up here. We let v equal y cubed. So we could substitute in y cubed is equal to 6x minus 1 all over 6 squared plus c over e to the 6x. So we solve the Bernoulli equation, or we solve this differential equation by using the Bernoulli equation, saying that if you do a substitution to make a differential equation, first order differential equation, you can obtain a linear equation and solve it that way, and then go back and substitute in what you originally subbed in, which was this v equals y cubed.